Hello, students. Today we will study about chemical reaction and equation 1, in which we will study about physical and chemical changes, balancing of chemical reactions, combination reaction, exothermic and endothermic reaction. Let us take examples and understand. A tree changes with every season, just like the changes we see in science. In spring, new leaves appear. This is like a physical change. The tree grows in size and shape, but its substance remains the same. In summer, leaves turn greener as photosynthesis works at its peak. Here, a chemical change is happening. Sunlight, water, and carbon dioxide change into food and oxygen, creating something entirely new. When autumn comes, leaves change color and fall. The drying and color change involve both physical changes in appearance and chemical changes as chlorophyll breaks down. In winter, the tree rests. Its outward look changes, fewer leaves, bare branches. A physical change, yet deep inside, chemical processes slow down to conserve energy. Just like the tree, the world around us is full of physical and chemical changes. Some only alter the look, while others create something new. Nature is the best classroom to understand these transformations. Let us take examples and understand. Melting of ice is a physical change where water transitions from solid to liquid, maintaining its chemical identity. In contrast, the corrosion of a spoon is a chemical change, altering the spoon's chemical composition as it reacts with oxygen and moisture, forming rust. These examples illustrate the fundamental differences between physical and chemical changes. Let us see about physical and chemical changes in next slide. Physical changes involve alterations in shape, size, or state, without changing the substance's chemical identity. Examples include melting ice or breaking glass. Chemical changes, however, alter the substance's chemical composition, resulting in new substances. Rusting iron or burning wood are classic examples of chemical changes. How can you identify if a chemical change has taken place? Well, chemical changes are not always visible, but they leave behind some important clues. Let us perform one activity and understand about chemical changes. Let's perform an activity. Take some amount of lead nitrate solution in one beaker and potassium iodide solution in another. Now, carefully mix the two solutions together. Watch closely. As soon as they are mixed, you will notice a yellow solid forming. Upon mixing lead nitrate and potassium iodide, a chemical reaction occurs, resulting in a noticeable change. The physical state alters as a solid precipitate forms, and the solution's color shifts to a bright yellow. These observations indicate a chemical change, highlighting the transformation of reactants into new products. Chemical changes are often identified by certain visible or sensory signs. First, we notice a change in composition. For example, when raw ingredients combine to form a new dish like pizza. Second, there can be a change in odor, such as when fresh food turns stale or eggs release a different smell when cooked. Third, a change in color is a strong indication, like when an apple turns brown after being cut. Fourth, we observe heat transfer or exchange of energy, such as the release of heat during burning of wood. Finally, chemical changes can be identified by the evolution of gases, often seen as bubbles or fumes in test tubes during reactions. These signs help us recognize when a chemical change has taken place. So, these are the indications of occurrence of chemical change. A question is coming up next slide. Rusting of iron is a chemical change as indicated by. You can pause and answer this question. Rusting of iron is one of the most common examples of a chemical change. When iron rusts, it changes from a shiny silver-gray metal to a reddish-brown, flaky substance. This permanent change in color clearly shows that a new substance has been formed, rust, which is chemically different from iron. That's why rusting is a chemical change. At the atomic level, rusting involves iron atoms reacting with oxygen and water molecules. This reaction forms iron oxide, a new compound. Let us see what is happening at the atomic level by this chemical change. Chemical reactions involve the interaction and transformation of reactants into products. Reactants, the original substances, undergo changes at the atomic level, resulting in new substances or products. This transformation is fundamental to understanding how different materials interact and change in various conditions. Let us perform an activity. Let us burn magnesium strip in presence of air and observe. When a clean strip of magnesium is heated in the flame, it burns with a bright, dazzling white light. This is because magnesium reacts vigorously with the oxygen present in the air to form magnesium oxide, a white ash-like powder. Now, a question will arise. How can we represent this chemical reaction on paper? Let us understand on next slide. To represent the reaction of magnesium with air on paper, we use a word equation and a chemical equation. The word equation involves naming the reactants and products, while the chemical equation uses symbols and formulas. This provides a clear, concise depiction of the chemical transformation occurring during the reaction. A word equation uses names of reactants and products, separated by an arrow, to represent a chemical reaction. For example, magnesium plus oxygen equals magnesium oxide. In contrast, a chemical equation uses symbols and formulas. Ng plus O2 equals NgO. Both methods illustrate the transformation of reactants into products. The equation Mg plus O2 transform MgO is incomplete as it lacks symbols like S, L, G, and AQ and the stoichiometric balance. Now, let us study about symbol and balancing of chemical equations on upcoming slide. Chemical equations provide detailed information about reactions. Symbols like S, L, G, and AQ indicate states: solid, liquid, gas, and aqueous. Concentrated and dilute solutions are specified, as well as gas evolution and precipitate formation. For example, 2NaS plus 2H2O, yields 2NaOH aqueous plus H2 gas, showing sodium reacting with water to form sodium hydroxide and evolving hydrogen gas. Chemical reactions can be represented in two ways: word equation and chemical equation. For example, magnesium reacts with oxygen to form magnesium oxide. In word form, it is magnesium plus oxygen equals magnesium oxide. Using chemical symbols, it's NgS plus O2 gas equals magnesium oxide. This illustrates the transformation from reactants to products. A question is coming on the next slide. The mixture of common salt and water formed during a chemical reaction can be represented by. Please pause and answer this question. The mixture of common salt and water forms an aqueous solution, represented as NaCl-AQ. This indicates that salt is dissolved in water, creating a homogeneous mixture. In chemical terms, NaCl-AQ signifies the presence of sodium and chloride ions in water, essential for understanding reactions involving ionic compounds. In the reaction, methane, CH4, and oxygen, O2, are reactants, producing carbon dioxide, CO2, and water, H2O, as products. Count the atoms: 1 carbon, 4 hydrogens, and 2 oxygens on the reactant side. 1 carbon, 3 oxygens, and 2 hydrogens on the product side. This illustrates the conservation of atoms. The law of conservation of mass states that matter cannot be created or destroyed. In a chemical reaction, the mass of the reactants equals the mass of the products. This principle ensures that the number of atoms for each element remains constant on both sides of the equation, maintaining balance throughout the reaction. In chemical reactions, the law of conservation of mass is not obeyed when equations are unbalanced. For instance, in the reaction, CH4 gas plus O2 gas equals CO2 gas plus H2O gas. The number of carbon, oxygen, and hydrogen atoms differ between reactant and product sides, indicating an unbalanced equation. Unbalanced chemical equations, like CH4 gas plus O2 gas goes to CO2 gas plus H2O gas, do not adhere to the law of conservation of mass. These are termed skeletal or unbalanced equations, as the number of atoms for each element differs between reactants and products, indicating an incomplete representation of the chemical reaction. Let us see how can we balance these chemical equations. A balanced chemical equation ensures the number of atoms for each element is equal on both the reactant and product sides. This adherence to the law of conservation of mass means mass is neither created nor destroyed, maintaining equilibrium in chemical reactions. In a balanced chemical equation, the number of atoms for each element is equal on both the reactant and product sides, adhering to the law of conservation of mass. Unbalanced or skeletal equations fail to meet this criterion, as they do not conserve mass, unlike balanced equations, which ensure mass is neither created nor destroyed. Balancing a chemical equation involves ensuring the number of atoms for each element is equal on both sides. We should follow some steps to balance this chemical equations. Begin by writing the correct chemical equation. Identify and count the atoms for each element. Choose the compound with the highest number of atoms and balance it first. Continue by balancing the remaining elements. For example, balancing FeS and H2OG to form Fe3O4C and H2G requires adjusting coefficients to 3FeS plus 4H2O gas equals Fe3O4S plus 4H2G. A question is coming on next slide. Identify the value of A in the given balanced equation. 2 magnesium solid plus O2 gas to A magnesium oxide solid. Pause and answer your question. In the balanced equation, 2 magnesium plus O2 gas equals A magnesium O. The value of A is 2. This indicates that 2 moles of magnesium oxide are produced from 2 moles of magnesium and 1 mole of oxygen. Observe 2H2 and O2 yield 2H2O, and H2 with Cl2 forms 2HCl. In the third equation, CaCO3, H2O, and CO2 combine to produce CaHCO3 2. They are showcasing the diversity of combination reactions. Let us study more about the combination reaction on the next slide. Combination reactions involve 2 or more reactants forming a single product. As A react with B to form AB, it represents a combination reaction. For example, carbon reacts with oxygen to produce carbon dioxide. So 2 reactants combine to form one product, so this is a combination reaction. Let us study more about combination reaction. Let's perform an experiment. Take a few spoons of quicklime and put them in a beaker containing a thermometer and mix it. Now we carefully introduce the solid quicklime into the water. Watch closely. The moment the 2 substances combine, a chemical reaction begins. As shown by the equation below, calcium oxide, CaO, reacts with water, H2O, to form calcium hydroxide, or slaked lime, CaOH2. We can observe two key features of this reaction. First, it's a combination reaction where two reactants form a single product. Second, if you look at the thermometer, you'll see a dramatic rise in the temperature. This tells us that heat energy is being released, marking this as a highly exothermic reaction. Exothermic reactions are defined as those that release heat to the surroundings while forming new products. Consider the common process of burning natural gas, or methane. The reaction with oxygen not only forms carbon dioxide and water vapor, but crucially, it generates a significant amount of thermal energy. This is why the heat term appears on the product side of the reaction equation, making it an essential and energetic class of chemical change. Now, let us see about endothermic reaction on next slide. In contrast to exothermic reactions, we have endothermic reactions, which are chemical changes that absorb heat from the surroundings. This image shows the decomposition of ferrous sulfate, FeSO4, a process that requires external heat to occur. As you can see, the reactant is heated over a flame, driving the formation of ferric oxide, Fe2O3, and the gases sulfur dioxide, SO2, and sulfur trioxide, SO3. The placement of the word heat over the reaction arrow signifies that energy must be continually supplied for the reaction to proceed. I hope you have understood about physical and chemical changes, balancing of chemical reaction, combination reaction, and exothermic and endothermic reactions. Let us summaries on the next slide. This chart summarizes the main concepts surrounding chemical reactions. A chemical equation represents a reaction using formulae and symbols. A balanced chemical equation adheres to the law of conservation of mass. Reactions can be classified by how they proceed. A combination reaction yields a single product from two or more reactants. Finally, reactions are categorized by energy change. Endothermic reactions absorb heat, while exothermic reactions release heat.